If you've been on the internet in the last few months, you've probably seen a fake image at some point, something generated by AI. Okay, first off, what do I mean by fake image, right? Well, what's a real image? What's a fake image? Well, today when I say fake image, what I just mean is an image that no one took a picture of, no human drew it, no person like had MS Paint generated by like layering things on top of each other. No, I'm talking about things where we wrote a computer program called a neural network, and that neural network made some image by itself that nobody's ever seen before, or at least hypothetically nobody's ever seen it. So I'm going to call those fake images, synthetic images, generated images, or just AI images. And today, what the question that I want to answer is, how do AI images work? Or how do we get images like the fox man here and the lady in the jungle here? How do we get what's called a neural network to generate these images based on us just telling it, hey, give me a picture of a fox with glasses? So the answer that I want to give today is reverse diffusion. It's not the only answer. There's lots of answers. I also don't want to like really give the answer. That is, like, there are a million little details, and I don't intend for you to need a background in linear algebra or machine learning to be able to understand what I'm going to explain today. So every explanation I give here should have the caveat that it's like at least a little bit hand wavy, right? Like we're playing a little bit fast and loose with the absolute truth here, but I hope I give you a good impression of how these things work. Now, to understand the reverse diffusion process that we use for AI images, you really ought to understand forward diffusion. What is forward diffusion? So basically, it's just adding a little noise to an image. So if you start with a clean image and add a little noise, add a little more noise, a little more, you keep adding noise over and over again. Eventually you get to just pure plain noise. No more image, Foxman gone. All we have is this Gaussian noise. That's forward diffusion. Now, reverse diffusion is that, but reversed. So start with pure noise, remove a little bit, remove a little more. See, you can make out his ears, his face now. Remove a little more, and remove a little more, and then bam, suddenly out of nowhere, we go from random noise, step by step by step by step, we reverse diffuse our way all the way to nice Foxman. So the key is, like I said, removing a little noise, but that brings up the question, what is a little noise, right? And how much do we want to remove? And how do we know what the right noise to remove is? So answering how much to remove is very complicated. I'm going to stick to like almost a thought experiment kind of explanation. So what we basically do is, really the diffusion process is continuous. What I mean by that is, like, hypothetically, we don't want to remove any like real amount of noise. We want to like gradually remove infinitesimally small amounts of noise. And if we were able to do that, everything would be so perfect, and we'd remove just the right, basically infinitely small amounts, and we get to a perfectly clean, good image. But we can't do infinitesimally small. We have to do some real amount. We also don't want to do lots and lots of times. We're using computers to do this. Sure, they're quick, but the more steps we make them take, the longer it's going to take. So for the sake of simplifying things, right now I'm just going to say split the process into 1,000 steps. And that is still how most of these models are trained. They're trained as if they are going to need to remove the noise in 1,000 steps. So they start with random noise, they remove a little bit, and then they do that 999 more times, and then that's when you get your clean image. So we split into 1,000 steps, and at each step, you're basically just trying to remove 1/1000th of the noise. Okay, that's kind of simple. It's wrong, but it's simple. Now, what noise do we remove? We know the amount. We're like trying to do like 1/1000th of the signal, kind of. But how do we know what that noise should be? You know, if I just remove random noise from random noise, I get random noise again. That's how random noise works. So I need to remove something purposeful from it if I hope to get, you know, a clean image at the end. And so what you see right here, I'll hide my face so you can see the figure credit. This is the original UNet. That's just the name of a type of neural network, but I really don't want you to care about the neural network itself. We are going to treat it like a black box. That means whatever's going on inside doesn't matter to you. You only care about what's outside. I want you to care about what the diffusion model or the neural network takes as input over here and gives us this output over here. That is, what do we need to give it in order for it to give us what we want? Well, like we've been talking about, reverse diffusion, we want to start with noise and eventually remove enough noise to get to an image. So the input's pretty obviously noise, and the output is obviously also noise. The difference is the input is the noise we have, and the output is the noise we need to remove in order to make progress towards our clean image. As an additional input, we like to tell the network, hey, this is the step we're on, right? Instead of giving it some noisy image and just having it guess at what step we're at, we tell it explicitly, step 1000, remember it's reverse diffusion, so step 1000 means we're at the beginning. Whereas after we've done 800 steps, step 200, we're pretty close to the end, and so we tell the network that. But at every single step, its job is just to take this noisy image and predict the noise. Then we are going to remove the noise, and after we do that a bunch of times, we'll get the original clean image. Or if we're trying to generate a new image, we'll get a new clean image that we've never seen before. Now that we know how diffusion works, at least at a high level, let's talk about why you would want to use these models. So we're going to do a little bit of history here, I guess, talk about some AI techniques that preceded diffusion-based image generation. The reason I want to talk about that is because it's a little hard to understand why we use diffusion without understanding there were things we did before. And also, these techniques are still used in diffusion. I'm not really going to explain too much about how they're used because that gets kind of complicated, but they're used, and so it's good to know that these things exist. And obviously, diffusion is kind of convoluted, right? You would think if this neural network is a black box, how about my input's just, hey, I want a fox, and the output is just a fox, right? Why all this, like, give it noise, predict noise stuff? And so I hope to give you some intuition about that. So let's get into it, right? Okay, so we have our neural network, and we need to give it some input, and we need to get some output. And so one idea that people had, right, we want new images as the output. So the idea was, let's train something called an autoencoder. What's an autoencoder? Well, it's two neural networks. Remember, they're still black boxes, don't care about what's going on inside of them. One neural network, its job is to turn an image into a code. That's the encoder. It encodes the image to code. What is a code? A code is just a bunch of numbers. So in this case, maybe my code is 127455963, as an example. In reality, the codes are tons of numbers. Like for a megapixel image, your code might be, like tens of thousands or thousands of numbers. The decoder's job is to take the code, and let me hide my face, is to take the code and then send it to the decoder. The decoder gives you that same image, the image represented by the code. And so this network's being trained to memorize, right? It converts images to codes and codes back to images. That code being a collection of numbers, what we hope we can do is, well, we take the codes that work for what we call reconstruction, or giving us images we've seen, and if we change them, still being code-like, but totally different numbers, hopefully we get an image that the network hasn't seen, right? New code, new image. That's the idea. So the decoder can both reconstruct if we give it a code it's seen. It can generate if we give it a code it hasn't seen. But in practice, it's really hard to balance these things. It's hard to get a network that gives you good quality while also giving you new things. But we want pretty things that we haven't seen before. So we need to balance these somehow. And GANs are an attempt to do that. So with GANs, what you're going to get is a random code. So instead of getting an image to code, we throw that part away, and now we're just getting random codes. Kind of like what we did to generate here, just random code-like codes. So we'll get a random code, we'll pass it to a network that's supposed to generate, and it'll give us some image. At the same time, we train a different network whose job is just to say real or fake. And the idea is that that both of these networks get better at their jobs together. The generator gets better and better at generating more and more realistic images, as the discriminator gets better and better at telling it if they're real or fake. What actually ends up happening, though, is that the discriminator has a really easy job, and so it gets way too powerful. It is much harder to generate a good image than it is to tell if an image is fake or not. And so why do we use diffusion? Well, it's really hard to get quality with novelty, and it's really hard to train in that generative adversarial approach I just showed you. And so diffusion basically just gives us newer images that look better while also being easier for us to teach the network what it needs to do. Now, we can still use autoencoders, we can still use GANs, but we use them in the framework of diffusion. So we use autoencoders to just make the diffusion model's life easier in a way that I'm not going to explain right now because it would take way too long. Save that for another video. And you can throw a discriminator in there. Just tell the diffusion model, hey, that looks real, hey, that looks fake. And it'll help the diffusion model learn to make images that look just a little bit prettier. So that is my quick, not so deep, I guess a shallow dive into AI images, and specifically how we generate them with diffusion models. Now, the explanation I just gave is very high level. It doesn't get into a lot of the nitty-gritty that really make these models work in real commercial applications. Like there are tons of tricks I didn't cover used by ChatGPT, for example, to give you some of those nice Studio Ghibli memes. But yeah, I hope this has given you a little better understanding of how some of these models work, and I hope to make more videos getting into some other topics, maybe even including some of the hairy ethical implications of some of this stuff, because I think that's pretty interesting. Anyway, thanks for watching, and hope to see you next time. Bye.